Well, welcome everyone to our seminar series of the ARA program. Today we're very happy to have Marcel Vonk. He's at the University of Amsterdam, which is where he actually started his career, research career, and went back to, after a few postdocs, one of each coincided with mine, and that's where we met and started actually collaborating. So he's worked on different applications of resurgence and asymptotics in mathematical physics, in particular in matrix models and topological strings. And we're very happy to have him today actually speaking about one of these topics, which is matrix models. So his topic is matrix models, asymptotics, transseries, theta functions, and all that. And I'm very happy to listen to it, because even though I'm part of the collaboration, I always learn something from your talks. Thank you, Marcel. Oh, sorry, just one thing. If you want to ask questions, unless you have some urgent question, please leave them to the end. And remember that you are being recorded and live streamed. So if you don't want to show up in the recording, do use the chat to ask your questions. I will be checking this. Thank you. Sorry, Marcel, you can go.
Thank you, Ines. And thank you all for being here and for inviting me to give this talk. I'm very happy to do so. I hope my screen is still visible. The green line around it disappeared, but I think you can see it. If not,
it's visible.
Let me know. Good, great. Yeah, so indeed, I want to talk about matrix models today, and in particular, everything they have to do with resurgence. So things like asymptotics, transseries, theta functions, and so on. Maybe before doing so Ines just introduced me, but I think it would be nice if I also introduced the people I'm working with, not so much for this project, but since September or so, we've had a little resurgence group that just started up in Amsterdam with not just me, but also Eric Lanen, who is interested more in the quantum field theory side of resurgence, and then 2 PhD students working on this, and a master student, Alexander, and Koenraad being the PhD students, and Kartik, the current master student, who's also applying for PhDs at the moment. So you might hear his name soon. I figured it would be nice to introduce our little group to you, and of course, hopefully in weeks or months or maybe a year from now, everything will be opened up again, and you're very welcome to come and visit us all in Amsterdam. So what I want to talk to you about today is not work with those people, but work with Ines and Ricardo Schiappa, which is a very long ongoing project that basically started already 10 years ago when we wrote our first paper on resurgence in string theory, 2011. And actually has been going on ever since, and also ever since we've been promising you to have been promising you a new publication about this. I already said at my talk in KATP in 2017 that this publication was around the corner, but well, I hope you haven't been excited refreshing the archive, because it hasn't appeared yet. But I just checked. We now have a folder on our Dropbox called Paper Final with capital letters. So it seems this paper is really going to be there in a moment. So that's one of the things I'll be talking about. So as for references, yeah, there's the old paper, there's the upcoming paper, and also there are the talks at KITP that I mentioned, where Ines and I both gave a talk about subjects related to this, where a lot of this already appears, but there will also be some new things. I'll mostly be very pedagogical today. I understood that several of you are interested in the topic of matrix models, but maybe not everyone is an expert in this. So at least the first half of my talk will just be a very slow pedagogical review of what matrix models are and how you can apply resurgence to them. So if you already know everything about matrix models, then feel free to go get a cup of coffee and come back in half an hour or so, because that's really going to be more of a review talk. And then the second half of the talk will be about the project with Ines and Ricardo. I won't be very good when it comes to further references. I will mention a few around throughout the talk, but of Of course, this is a very big topic that people have been working on for 40 or 50 years, maybe already. So there are a lot of references, and I refer you to, in particular, the first paper where we mention a lot of the references where things can be found. So here's the plan for today. Like I said, I want to start very basically with just telling you a few things about the basics of matrix models and why, as physicists, we're interested in them, but also as a mathematician, you can be very interested in them. I want to tell you about how to solve the matrix model. There are two classical ways to do so, one using spectral curve methods, the other using orthogonal polynomial methods and something called the string equation. In particular, the second one will play an important role here, but the first one as well. So I want to tell you a little bit about both methods of solving matrix models. And then we really want to go into resurgence. So I want to tell you that there's a transseries solution to this matrix model. This was essentially what we constructed in 2011. And then I want to go towards how should you look at this transseries solution? What can you learn from it? And does it describe the entire moduli space, for example, or is it only valid in certain corners? And this will lead us to a little trick that's very useful to study these transseries, which we dubbed quadratic summation or quadratic transasymptotic summation, modeled after a method that Ovidio Costin and his collaborators devised earlier for example, Penlevé, but this is a quadratic variation. I'll tell you what the quadratic means. Then I also want to tell you a little bit about how all of this relates to theta functions. You've seen the word theta function appear in the title of my paper, and there are very intriguing relations to other ways people have studied matrix models through theta functions. So that'll be the last topic of today, and part of that is still work in progress, so I might be a little bit hand-waving there. And then in the end, I'll conclude and end with some open questions. So that's the plan for the next 15 minutes or so. So let's start with the very basic. Why matrix models? What do I even mean by matrix models, and then why are we interested in them? Well, the answer to that depends a lot on whether you're a physicist or a mathematician. I'm mostly a physicist, I would say, so I'll give you the physicist's motivation. And the main reason to be interested in integrals over matrices is that they're a nice step in between something that may be a bit too simple and something that may be very interesting but too hard. So in quantum physics, in the end, what we want to do is path integrals, the path integrals you find in quantum field theory. And those are integrals over entire field configurations. So the space you integrate over actually is mathematically maybe not even that well defined. It's a space of all configurations of a field, and therefore it's a highly infinite dimensional integral, and that's very difficult. So you might say, well, maybe as a toy model, I start by studying ordinary integrals and see what I can learn from there. But ordinary integrals over simple numbers are maybe a bit too simple, and they cannot easily accommodate physical things like phase transitions, for example, that we'll be very interested in later. And so there's a very nice step in between where you say, well, I still want to integrate over a finite number of variables, but I want to put these in a matrix and then let the size of the matrix go to infinity, and in this way, well, find more interesting physics. And so that'll be the idea of today. And this turns out to be a very nice physical idea. Like I said, people have studied matrix integrals like this for many decades already. They appear as toy models in physics. For example, if you want to study gauge theories, then your quantum fields are already matrices. And so you might say, well, what if I keep the matrix nature but forget about space-time? So I do a matrix integral. Can I learn something? And you definitely can. There are toy models for quantum gravity that triangulate space-time, and then the triangulation appears to be nicely encoded in a matrix model. So there are many toy models in physics that make use of these matrix models. There are also dualities to maybe more physical models, where I'm not talking about the standard model or anything, but for example, topological string theories turn out to be dual to certain matrix models. And so there's a whole class of problems that you could apply this to. And the reason physicists are so interested in them is that they're rather rich models. And in particular, today we will see that these models has things like phase transitions and display different phases. And that's something that's not only very interesting, but also something you might want to describe, and something that resurgence might play an important role in describing, because you really want to go from one domain of validity of certain parameters to another domain of validity. And this is something that we know traditionally resurgence is very good at. So that's the point of view I want to take today. So here's the type of model that we want to study. So we want to do some integral, I hope my mouse is also visible, over entries of a matrix. And then we want to do a very simple integral like the quartic integrals we saw in the school earlier, for example. But now, of course, everything depends on the matrix. So you take some potential. We want to take it very simple. We want to take the potential V to be maybe just a quadratic or maybe just a quartic potential with one small anharmonic term. And then you want to take the trace and integrate over the exponential of that. So that's the type of integral we're interested in doing. So here I've drawn this particular potential that we want to see as an example. But let me immediately stress with that in our talk today, everything will be complex. So if I draw a potential like it is a real potential here, don't take that too seriously. In particular, don't really think of a minimum sitting in the middle and two maxima sitting outside. All of these are saddle points, but of course, in the complex plane, they have a direction where they go up and they have a direction where they go down. So you might think of this as a potential where particles want to sit in the middle because that's a local minimum. But particles might just as well sit at the outer maxima because those are saddle points as well. And we'll see that happening later on. So the parameters of this model, they're not that many, but there are enough to make it interesting. Of course, there's the size n of the matrix. Then there's this overall normalization constant that I put in front of the potential, which you can think of as a physicist as h bar, for example, as Planck's constant. But in relations to string models, it's also often identified with a string coupling constant, which is why I will call it GS. And then, of course, there are any parameters that you have in your potential. Here there appears to be one. So there's this variable in front of the quartic term that I want to be able to vary to get different quartic potentials. But at the same time, you can, of course, rescale x or rescale m, and then the quadratic term behaves differently from the quartic term. So you can put this lambda behavior in the end in the GS. So by rescaling parameters, you see that GS and lambda are not really independent variables, but that you can quite easily scale one of them away. And so I usually choose to scale lambda away and express everything in terms of either n or GS. And then finally, like I said, we're interested in limits where n becomes very large. And usually you can do two things. You can just send n to infinity, or you can send n to infinity, keeping something fixed. Physically, it's usually interesting to keep the product of n and GS fixed. So this is called the 't Hooft coupling in physics. And then expand in the variable that you have left. So you expand either in small GS or in large n, keeping t fixed. And so everything that you compute will be a function of t. And so this is what will lead us to asymptotic expansions, things growing factorially, and that's what will lead us to resurgence. Now, this is not quite all the parameters that we have in our model. And the reason is that I haven't really told you how to integrate over all matrices. I've just said I want to integrate over matrix entries. But of course, what you can integrate over depends a little bit on the potential. So for this quartic potential, for example, you would want to have an integration such that this quartic term dominates at infinity, right? So you want to integrate in certain directions in your matrix space. Well, here for this example, you can do this by integrating over Hermitian matrices, for example. But then you already see that you're not going to integrate over any matrices, right? The set of Hermitian matrices is sort of half-dimensional in the space of all complex matrices. So you want matrices in this case that have real variables on the diagonal and then complex conjugate variables of the diagonal. And so you want to integrate over n squared real degrees of freedom. So for example, the real and imaginary parts of the upper of diagonal triangular matrix, and then the real parts of the diagonal elements. But you can also see that if you want to generalize this to some weird potential, that's going to be very hard. It's not always going to be Hermitian matrices that work. And so you need a bit of a trick to find good manifolds to integrate over. And the trick is to diagonalize, let's say, this example, and then from that diagonalization, learn what you need to do in general. And this is a very classical way to deal with matrix models. So you can find lots of information about this in all sorts of textbooks. The idea is, of course, that there's a big symmetry here. So if I have a potential that I take the trace of, and the potential is a polynomial, then of course, if I replace M, let's say it's Hermitian now, by a unitary matrix times M times its inverse, then this trace doesn't change. And so there's a big symmetry. I have the integral over all matrices is in a sense an integral over angles that sit in this unitary matrix and over eigenvalues. And this integral over angles doesn't do much, right? It's just a constant factor. So you can imagine that you can first integrate over these angles and then leave the eigenvalues as the true variables that you want to integrate over. And you can indeed do that. And so if you do that computation, you get the formula that you see in the middle here, where you still integrate over something dependent over the potential, but now only the potential of the eigenvalues. And the only thing that comes out of this computation is that you cannot just ignore the integration over angles, but they have some sort of Jacobian if you change variables to angles and eigenvalues. And the Jacobian turns out to be the Vandermonde determinant of the eigenvalues. So just the product of the difference of all the eigenvalues. And it's called the Vandermonde determinant because you can also write it as a determinant where you put ones in the first column, then the eigenvalues in the second column, the squares of the eigenvalues in the third column, and so on. And so this formula is really the starting point of what we call matrix integrals. It's not really an integral over n squared variables, it's always an integral over n variables. And now, of course, you can cook up a very complicated potential if you want to. And you can say, well, I just want to choose my integration path such that if I go off to infinity, this exponential decays. So that'll give you a much nicer way to define the possible integrations, but that's not unique. So as you see in the picture here for the quartic case, there are 4 directions that you can go off to at infinity in general for a quartic potential, such that this exponential decays. And so there are actually extra parameters here because you can choose how to integrate. You integrate from one infinity to the other, but there are 3 linearly independent ways to do so. So a physics remark that I want to make here that will be important in a moment. This Vandermonde determinant, it makes life hard, but it's also quite nice physically. You can see that if you don't write it as a prefactor, so this looks a bit like what physicists would call a correlation function, but you can also write it as the exponential of the log of the Vandermonde determinant and think of it as something that belongs in the exponential, something that belongs in the action. And if you do that, then you see that if you want to write equations of motion, for example, this Vandermonde, of course, goes to 0 if 2 eigenvalues become the same. And so it becomes the exponent of minus infinity. And this means that the eigenvalues do not want to sit next to each other because they will need infinite energy for that. So the eigenvalues repel a little bit, and so they tend to form extended structures in the complex plane. They don't just all want to sit at one point. Yeah, so this is how we now want to define a matrix model as an eigenvalue integral over n variables. And now you can already do some tests or some computations if you want, because of course, even before doing the full integral, you could say, well, as a physicist, I'm probably first interested in the classical configuration. So I want to study the saddle points of this integral, see what the configurations at the saddle points look like. And this is already enough to show you that there must be some sort of phase transitions going on in this model, because what these saddle point configurations look like depends a lot on the variables of your other parameters, and in particular the variable t, this hoofdcoupling n times gs. So let's just do some numerical example. Let's fix n, fix also the argument of t. So I want to change t in the complex plane, but I'll fix the angle and just increase the size of t. And I think I fixed n equals 100 here, and this is what then happens. So if t is very small in absolute value, The repulsion term is very small compared to all the other terms, and so all the eigenvalues want to sit at one of the three extremal points, and I've chosen it here in such a way that they want to sit at the outer 2 points. And then if I start increasing t, like I said, they will start repelling more and more and form these structures. So this is still one particular phase of the model, but now at some point you see that the eigenvalues actually also start occupying the third point. In physics terms, the Fermi seas of the 2 outer minima have filled up, and now the third one also starts filling. And so you start to see the extra cuts growing, but then at some point the 3 cuts even touch each other. This is what just happened when we went from green to red. And now you see that even a more interesting structure appears where the eigenvalues tend to sit in these trivalent diagram-like figures. So you clearly see that there are different phases at work here, and so this might be an interesting model to study if you're interested in phase transitions. A bit of small print, I also wrote it on the slide here. I'm not really computing saddle point configurations here. I'm using a trick where I compute zeros of orthogonal polynomials. But for many models, there are theorems stating that those actually, in the large n limit, do give you back the zeros. But it's just a faster way of computing these structures. All right. So yeah. So there's different phases, and you can even draw a phase diagram in the t-plane, and here you see it. So what we just did was we started at t equals 0 and then went through a phase where we have 2 cuts of eigenvalues, then went into this green phase where we have 3 cuts. I call that the anti-Stokes phase for a reason that will become clear in a moment. And then at some point you end up in this phase where you have even the trivalent diagrams. And what we'll see today is that in each of these phases you need different methods of computations, and also that resurgence is going to be very important to relate these different methods. So, well, those are just pictures, but how do you solve such a matrix model? Well, like I said, there's 2 classical approaches to doing so, one using spectral curves and the other using orthogonal polynomials and the string equation. And for us, it'll be the second method that's the most important, but at the very end of the talk, the spectral curve will also pop back up again. So I want to say a little bit about both as sort of the second half of this review part of the talk. So let's first look at the method that is maybe of least interest to us right now, which is using spectral curves. And so here the idea is basically to elaborate on the movie that I just showed you and really study in the large n limit how the eigenvalues behave. And in the n to infinity limit, of course, this becomes something continuous. And so you might try to compute an eigenvalue density that I call the rho of z here. So it's what happens in the limit n to infinity. If I take a delta function essentially at the location of each of my eigenvalues, and I divide by n, and then I try to send n to infinity and see if I get some nice classical function. Well, of course, this is never going to be a very nice function because the eigenvalues tend to sit at cuts, at lines in the complex plane. And so it's still going to be something that has like a delta behavior at these lines. It's going to be 0 everywhere except on lines. And so it turns out to actually be more interesting not to study this eigenvalue distribution itself, but the related resolvent. So resolvent is a thing that you might know from many different branches in mathematics, and it's very useful here as well. So what you do essentially is construct a different function which has branch cuts at these locations where the blue lines are here, for example. And it turns out that to do that, you need to study the trace of 1 over z minus the matrix. And if you do that, you get a much nicer behaved function, which is nice and smooth and continuous everywhere, except at these cuts where it jumps, and it jumps essentially by rho. So it's a much nicer way to package the information about the eigenvalue density. And the main reason it's nicer, and I'll go through this quickly because I don't need it in a lot of detail, but the main reason it's nicer is that this resolvent in the true large n limit actually solves an algebraic equation. So you can now actually write down the equations of motion, the saddle point equations for the eigenvalues, take the large n limit, and you will see that all terms with derivatives and so on cancel out, and that you get a very nice simple quadratic equation for this resolvent. So that's an equation that's easy to solve. It's not completely straightforward because there's this unknown function f of z that's sort of implicitly given in terms of the eigenvalue density. But what is nice, at least, is that everything here is polynomial. So also v prime, of course, the derivative of the potential that appears is a polynomial. And you can show that this f is also a polynomial function in z. So this g actually lives on a hyperelliptic curve, if you want. It's a quadratic equation in g and a polynomial equation in z. So, for example, for the symmetric quartic, this is actually a very nice and simple hyperelliptic curve. It even turns out to be an elliptic curve in disguise. So it is hyperelliptic, but it's a double cover of an elliptic curve. And so you can imagine that you can use this curve and this resolvent to do computations. So I will not go into the details of how to do this computation. I just want to show you this picture of the curve. But it turns out that everything classical, so everything really in the large n limit, can now be computed. So you can compute the filling fractions, how many eigenvalues are in the different cuts. But you can also compute the free energy of the model, so the logarithm of the integral that we're interested in a very simple way, basically by just doing contour integrals of g dz over certain closed contours on this spectral curve. So this is one method that people have used a lot to solve the model. But when I say solve the model, of course, everything I've said now is really in the large n limit. And so this doesn't tell you much about 1 over n corrections or GS corrections. And those are, of course, the ones we're interested in, because those will give us the asymptotic series. So there are many ways to do this also from this point of view, and I'll not go into that, but I just want to tell you that the way I want to approach things is not the only way. You could start from this curve and produce asymptotic series. You could do topological recursion a la Hénard-Orentin. You could use WKB-like methods, exact WKB-like methods. You could use the dualities to topological strings, and so on. So there are quantum corrections also in this approach, but that's not the way I want to go. By the way, if you Google for quantum corrections, you'll find the picture I showed here. I'll let you guess what kind of company has this logo. It has nothing to do with quantum physics. It's actually a company that does car repairs. So I want to go the other way. I want to use a different methods of solution. So we start again from our matrix integrals. And for now, and I'll come back to this later, but for now, let's assume we just pick one of these contours of integration that works and integrate all of the eigenvalues over that contour. So the other trick to solve matrix models is to introduce orthogonal polynomials now. You notice that this integral is really just doing a lot of the same integrals. They're all of the very same form over every zi. And so you might say, well, most of the physics is in this exponential, but of course I have this Vandermonde to worry about. So how can I compute this expectation value of the Vandermonde? Well, the trick is to introduce orthogonal polynomials. So you introduce polynomials, Pn of z. The n labels the degree of the polynomial, and I wanted to start with a 1. So z to the power n, and then lower order terms that may have non-unit coefficients. And I want to construct polynomials in such a way that when I integrate them against this exponential, they're orthogonal. So I want Pn and Pm integrated with this d mu that has this exponential in there and the 1 over 2 pi. That it gives 0 if I take two different ones, and it gives me a number, non-zero number, if I take the same. And of course, that non-zero number doesn't have to be 1. So it's not orthonormal polynomials because I already picked my leading coefficients of the polynomial, so I have no scale invariant. So that coefficient is then going to be some number h. And actually that turns out to be very nice, because now once you've done this, you can very easily express the full partition function in terms of these coefficient h only. And this again is a standard trick that you can find in the textbooks. The trick is to realize that this Vandermonde determinant can actually also be thought of as a determinant of all orthogonal polynomials, right? If I write 1 in the first column and z in the second column, then I can also add the first column to the second one some number of times, and that won't change the determinant. So I can actually write any monic degree 1 polynomial in the second column. And similarly, I can add the first and the second column to the third column and write any degree 2 polynomial that starts with a 1 there. So in particular, I can write all the orthogonal polynomials. And then, of course, orthogonal polynomials are nice because they're orthogonal. And so in this square of the Vandermonde, many terms will cancel. And if you do the computation, then you end up with a very simple answer that the partition function is just the product of all of these numbers Hn. So the goal, if you study matrix models, is essentially to compute all of these numbers Hn. And once you've done that, you're pretty much done and you know your answer. So that will be our goal as well, to find these Hns. But of course, they are functions of GS in particular, and they might be functions of the quartic coupling and of the size of the matrix as well. So the textbooks then continue by saying, well, all of these integrals, they fall off exponentially, and so you can use partial integration, and you can find all sorts of word identities. So you can use the statement that an integral over a total derivative, if it goes off to infinity, is 0. And you can then try to put orthogonal polynomials inside your integral in such a way that the total thing is a total derivative. And then using orthogonality, you can derive relations between these coefficients Hn. So if you do that computation for this particular case of the quartic potential, you will find the equation that I wrote here. And so it's not directly the Hns that appear in here, it's actually the ratios of Hns, Hn over Hn minus 1 that I called Rn. But if you do that, then from these word identities, you find that these Rns satisfy a very simple recursion relation. So once you know the first one, let's say N0, R0, then you can compute R1, and then you can compute R2, and so on and so on. So you can recursively compute them. Then, of course, since these R's are the ratios, you also need to compute one H, but H0 is also very easy to compute. It's just an ordinary integral. It's the 1-by-1 matrix model if you want. So that's also easy. And so, yeah, the entire business of solving the matrix model is actually solving this recursive equation. And that equation will also be the starting point for us. So now let's slowly start leaving the textbooks and go towards resurgence. So this is not really an equation yet that we can, for example, plug a transseries into. And what we would really want to do is say expand things in GS, first perturbatively and then maybe as a transseries. But for that we need something that depends on GS on the left-hand side as well. And so there's a simple assumption you can now make. GS is small anyway, and I'm going to need a lot of these Rn's, right, or capital N of them. So what if I now, instead of this index n, multiply it by GS? So this will be something that makes very small steps, and then consider this x as a continuous variable. In other words, what if I rewrite the equation on the top as the equation in the blue box, where now, for example, Rn plus 1 becomes capital R of x plus GS. Well, here I haven't done anything, I've just rewritten the equation, but of course now there's a crucial assumption, which is, can we find a solution in such a way that this R actually becomes a smooth function of x, so that it's not only defined at these discrete intervals, but maybe for any x. If that's the case, then I can start perturbing in GS and find a series solution, find a transseries solution, and so on. So that's what you want to do now. Before just closing our eyes and doing that, however, especially if you're a mathematician, you might now feel a little, well, not very much at ease, because I'm making quite an assumption here, right? I'm really making the assumption that these Rn's become something continuous and even smooth, and well, that's might not even be justified. So let me spend a few words on that. From a physics point of view, it's kind of natural that indeed you do get something smooth, because what does it mean if I have computed all of my Rn's and I want to compute Rn plus 1? Well, it means that I'm computing the matrix model with one more eigenvalue in there. So it's like adding a single particle to your system. And if I have a system that consists of many particles, then you would indeed expect that adding a single particle is something that leads to small changes. So from a physics point of view, it might seem like something smooth, but even from this physics point of view, you may already worry, because what if I'm in a phase where the eigenvalues cluster into two cuts, right? The blue picture that I showed at the beginning, where the eigenvalues sit in a left cut and a right cut. Then adding one particle is not really something smooth, right? Because then I have to make a choice to add it either to the left cut or to the right cut. And only adding two particles is really something that you can do in a nice, smooth and continuous way and repeat over and over again. And this actually turns out to feed back into the mathematics. So the assumption that I'm going to make, that R is something smooth, is really only true if you start from the one cut phase. If you would start from the two cut phase, you actually need a separate R for the even ends and a separate R for the odd ends. And so you will get two transseries, and they will be smooth by themselves, but the jump from even to odd is definitely not smooth. And if you're interested in more about this, I can refer to a nice paper by Ricardo Schiappa and Ricardo Vaz, who worked this out, who worked out these transseries for the two cut phase of the matrix model. But well, for us, let's just start from the one cut phase and be happy about having a smooth R. And our question will be, what about the other phases? Can I go, for example, into this green phase, into this three cut phase, or the phase that I will call the anti-Stokes phase? And as we will see, we can do so, even though this R becomes rather wild. The continuous formulation will still work nicely. And to see how wild it becomes, here are some further numeric examples. So what I plot is Rn here. So the horizontal axis everywhere is pretty much n. The left plot is the real part and the right plot is the imaginary part. And I go out in the phase space in two directions, one going through the one cut phase and one going through the two cut phase. So the first thing you see is indeed that all of the Rn's lie on a nice smooth curve if I am in the one cut phase. And you also see that if I'm in the two cut phase, indeed I need two functions to describe the behavior. So if you would zoom in, then the R's would jump from the lower contour to the upper one, to the lower one, to the upper one, and so on. But you also see that as soon as these curves start filling the third cut in the middle, then these Rn's become, well, what seems completely erratic, and they stay like that pretty much forever. Now, the point of my story is, of course, going to be that this is not erratic, that we can actually write nice functions that even describe this very erratic looking behavior. But that will require some work, of course. So in today's talk, I will not say much about this red phase, about the trivalent phase, but just to show you that indeed something is going on there as well. These plots are for generic integration contours. If you pick them very wisely, if you pick very specific integration contours, then you can see another phase transition occurring when you go into this trivalent phase, where indeed the Rn's become regular again. And so then it's only this anti-Stokes phase that really has this erratic-like behavior. So this is what we want to describe, and this is what we want to understand using resurgence. And so then, well, if you're a fan of resurgence and you see an equation, whether it's a differential equation or a finite difference equation like here, of course, the first thing you want to do is plug a transseries into it and see how far you can get. And so that's exactly what we did in 2011, and we were not the first ones to do that. Well, we were the first ones maybe to build the full transseries, but this already continues on perturbative work by Bassis, Itzigson, and Zuber, and then the one parameter transseries was already constructed, a big piece of it by Marcos Marinho. So what we did was give the full transseries to it. And so you start simple. You say, well, let's first not do any GS corrections, just pretend that this GS is not there. And so then this equation becomes very simple. And so you see that to leading order in GS, R is just this simple function of X. And this is actually the function. I don't know why I wrote two R's in here. That's a typo. But R is just 1 minus the square root of 1 minus 2x. And that's exactly the function that I plotted here in the purple region, for example. And then you can continue and say, well, now let's try a power series ansatz. So let's say that I have this leading behavior, but let's correct it with GS corrections. First thing you notice is that you need even powers in GS because this equation is completely symmetric in GS going to minus GS. So you might even expect that a solution also has that symmetry, and it turns out to have that. This will change in a moment, but for now, indeed, the perturbative series is just a series in GS squared. As a technical remark, everything, of course, depends on X. Remember, X was the N, right? N times GS. So X tells you which R you're studying. But it turns out to be easier to not express everything as a function of X, but actually take this first R that you find as a new variable and express all the higher RGs in terms of this small r. So all the expressions you will see from now will not be functions of X, but will be functions of R. And so you can compute. The first one is, of course, the R that we've already computed. It turns out that the first correction is R over 6 times 1 minus R to the 4th. You can compute the next corrections and so on and so on. And if you go on computing for a while, then you will find that this is indeed an asymptotic series. So these grow asymptotically. You also already see that there's a nice singularity in here. And what we've learned from this workshop, I think, is that singularities are not something bad, but actually something nice. In this case, there's a singularity at R equals 1. Which if you translate it into the phase space, it's this point at the very right edge of the one-cut phase. And that's actually a point where it's known that the matrix model itself becomes singular, but you can double scale it, and it will give you the Penlevee-1 differential equations. There's a similar point at the end of the two-cut phase, by the way, where you can get Penlevee-2. That you don't see from the perturbative series yet, which is not that strange because, like I said, we perturbed around the one-cut solution, but we will see that one appearing soon as well. So then you continue. We've now constructed the perturbative solution, and you might say, well, what about a transseries? These coefficients grow asymptotically, so I'm probably going to need a transseries. So what if I don't just take my perturbative sum, but I try to find some instanton monomial e to the minus a over GS, of course, because it has to be non-perturbative in GS. The A might still depend on X, and it will depend on X. And then build a transseries using not just powers in GS, but also powers in e to the minus A over GS. Can I solve it like that? And the answer is again, yes. You even find a free parameter, so any instanton monomial can be multiplied by an arbitrary parameter, which is also nice because we want some parameters. We have a second order finite difference equation, so we might expect two free constants. Well, here at least we find one. And so you can do this. You can just turn the crank and compute coefficients. One thing you will notice then is that now all powers of GS appear. So whereas first in the perturbative solution we had only even powers of GS, we now have them all, and this is a nice physical interpretation because this model, like I said, is dual to string theories. And in string theories, we have open strings and closed strings. And closed strings are usually what you find in a perturbative theory, whereas open things are what you find in non-perturbative effects when you have D-branes that strings can end on. And these strings, these open strings, turn out to have a coupling constant, which is the square root of the coupling constant of this closed string. So the upshot from physics is that in non-perturbative effects involving D-branes, you expect expansions in the square root of the expansion parameter that you had in the perturbative part. And that's exactly what you see happening here. So this is a nice consistency check with physics. You might now be worried that this breaks this symmetry, GS to minus GS, and indeed it does. And that will be restored later when we write down the full transseries solution. So you turn the crank, you start computing these RNs, but of course, before you do that, you need to compute this A itself. And well, it's not a hard computation. The expression isn't very elegant, but I've written it down here. It can again be expressed in terms of this R. And here already you see that you will find two possible answers. So you might wonder, which one do I pick? And of course, there's a good choice and there's a bad choice. The good choice is such that indeed my instanton monomial is a small correction. So I want A over GS to have a positive real part, and this turns out to fix one of the pluses. But you might also say, well, I'm not worried about convergence. I maybe want to write a trend series where I introduce both of them and never worry about convergence at all. And then you see that you should write both of them, and that will give us a 2-parameter trend series. In most of this talk, I will just pick this one, let's say, good value of the excellent, but I'll say a little bit about the 2-parameter trend series as well. This already tells you something about this phase space, because I haven't told you before how do I get the boundaries of these phases, but now we can get one. Because what happens at a phase transition? Well, this instanton monomial actually becomes important. So if I go back to the full trend series, I'm expecting here GS to be small and e to the minus a over GS to be even smaller, and then I have a good trend series description. But at some point, of course, a will vary as a function of x and therefore as a function of t. And so at some point, this exponential might actually become of order 1. And it turns out that this is exactly the point where the phase transition occurs. So if you draw the line where the real part of a over gs equals 0, then you get exactly the boundary of this one-cut phase. So up until there, the one-cut approximation is good. After that, you need to think. And then you can do all sorts of large order tests. We did that in our 2011 paper, and you can show that indeed the A that you find, for example, indeed describes the large order behavior of the perturbative coefficients. So in this plot you see in red the A is a function, and in blue the large order behavior that you would expect of the actual RNs, and you see that it all matches nicely. So resurgence actually is nicely at work here. Well, you turn the crank further and you say, well, I can now compute one instanton coefficient, so the perturbative coefficients around e to the minus a over x. And here you actually see something nice, because, well, the functions themselves may not be that interesting, but again, let's look at the singular points. Well, there's still one at r equals 1, but now a new one shows up at r equals 3. And this r equals 3, if you translate it to what t is, that is actually this Penlevet-2 point. So even though we started in the one-cut phase, if we start doing instantons and doing non-perturbative physics, we already see this Penlevet-2 point sitting at the end of the 2-cut phase. So this tells you that you're on the right way, that resurgence actually helps you in learning about much more about the phase diagram than just the one-cut phase that you started from. So then in 2011, we turned the crank all the way to the end, and we said, well, let's now construct this 2-parameter trend series, including both the plus a and the minus a, and it turns out that even you need some logarithms. And then you get a slightly complicated, but still very computable trend series that now has a parameter sigma 1 and a sigma 2 in there, multiplying the e to the minus n a over gs, but also the e to the plus m a over gs sectors. And well, you can then compute perturbative corrections around each of these sectors if you want. They have a nice generic form, and like I said, there are also some logs in there, but the precise form of what I'm showing you here doesn't matter much for us, but I just wanted to show you that you can compute anything you want now. To compute everything you want, maybe a quick remark, you have to be clever, because if you just plug this into a computer and then try to compute many orders, then you won't get very far, because you will get things like the exponential of shifted instanton actions, right? The string equation has x plus gs in there, and so you need to plug x plus gs into everything. And so if you just try to compute exponentials of this form by first expanding a and then expanding the exponential, you will get stuck very fast. So you have to be clever and use some tricks, and I'm including this slide for people who, maybe there are students in the audience who want to get into these types of computations. So to those of you who want to do that, I want to tell you, don't just expand everything brute force, because that doesn't work. So what do? Well, you take a GS derivative, for example. If you take a GS derivative on the left-hand side and on the right-hand side, then on the left-hand side, you will get the same exponential again. Then you can plug back the left-hand side, the right-hand side into the left-hand side, and you will get a recursion relation between the seeds. So by taking clever derivatives, you can get recursion relations for coefficients, and that's much easier to solve. Then you have something where the times grows quadratically instead of exponentially. And then you can compute hundreds of orders. So that's just a side remark. So now, what can you do? Well, this is great as long as you stay within the one-cut phase. And here I've shown you a picture. So I'm zooming in on a little bit of the phase diagram, and I want to follow this gray path here and see what if I now just sum the transseries. I do some Borel-Écalle summation or Borel-Padé-Écalle summation, or I go to the talks of Gerald and Ovidio, and I do more clever things, but I do some sort of summation. If you do that and compare to the actual RNs that you can compute using the recursion relation numerically, then you see that within this purple phase, the red line gives you the summed Borel-Écalle sum transseries. The dots give you the actual numerical results, and you see that everything matches very well. And you can match even up to as many decimal places if you want. So 20, 50, 100 decimal places, no problem whatsoever. But then as soon as you leave the blue phase and get into the green phase, you see that things go wrong. And so here the gray lines that you see are, I think, just the perturbative series Borel summed, and then the perturbative plus 1 instanton Borel summed, and then the red line is perturbative plus 1 instanton plus 2 instanton. You see that you get nowhere. You get a little bit outside the purple region, but then it starts going very bad. I took a case here where on the other side, I actually went through a Stokes transition and my non-perturbative parameter is 0. And then of course everything works, right? If I am in the situation where the non-perturbative parameter is 0, then I'm just studying the perturbative series and then it works. But as soon as you turn on this sigma, everything goes wrong. And so here we come to more recent results. I see I only have 5 minutes, so I'll speed up a little bit. Because now, of course, the instantons take over. They become of order 1. And so you want to do something to be able to see what happens in this green phase. So you want to sum maybe over instantons first. And that indeed turns out to be the trick. And this is not a new trick. If you look up old papers by Kostin or Kostin and 1, they already did this, well, what is it, 15 years ago, for the Penlevey equations, where they called it transasymptotic summation. So exactly this idea of maybe not treating instanton sectors as separate and just doing the Borel summation in the perturbative direction, but maybe first summing over instantons and then looking at GS corrections. And in these examples, you can do that very nicely because the n instanton sectors always grow like GS to the power n, essentially. And so you can try to find closed forms for the leading coefficients, for the instanton, for the RNs, but maybe also for the free energy, and just compute, and that works nicely. Here we can also do that. So for the free energy of the matrix model, you can again write the leading coefficient of the K instanton sector in closed form. And well, the closed form doesn't look very nice, but it is a closed form nevertheless, and you can sum it, and you find already an expression that looks a lot nicer. So this is a sum over all instantons, but at leading order in GS. And now if you look at where does the instanton action appear, well, the e to the minus a over GS sits in sigma, which I actually called it sigma hat here. So I pulled it into sigma and called the combination sigma hat. Here, so it appears in psi. So there are only 2 psi's in here. So if I now look at the true partition function, the exponential of the free energy, then this log goes away. And so I don't get an infinite expansion in sigma. I get 3 terms. I get a 1, I get a psi term, and I get a psi squared term. And so you find a finite polynomial expansion in sigma. And that's a hint that for these matrix models, you should really do something else. You don't want to sum polynomials, because summing a polynomial is the most stupid thing you can do, because you get a polynomial back. You want to sum infinite series. And so whereas for the free energy, this is a very clever trick and it works very well, for the partition function, you need a bit more. And that you can see if you look at how the partition function actually starts. The instanton sectors in the free energy start at gs to the power n, essentially. But if you compute it, then the instanton sectors for the partition function start like gs to the power n squared. And so you might wonder, can I now sum all of these? Can I sum quadratically in some sense? So not sum along lines, not sum like I did for the f, but sum all of these squared terms. And you can do so. So here I just wrote the closed form of the partition functions, and the thing that you should notice is the gs to the k squared here and the gs to essentially k squared here. There's a slightly different formula for even and odd sectors, but that doesn't matter much. And so you can sum these. You might be a bit worried because the coefficients seem to grow very fast. There are Barnes function factors in here. But there's also things that go to the power k squared that are small, and it turns out that it takes a long time for these Barnes functions to diverge. So numerically, there isn't really a problem here. You can solve. You can sum many of these terms. And this works very nicely. So even if you would not do the quadratic summation, if you would just do the linear summation for the free energy, then already you get the plot on the left hand side here. So the red line now is this linear summation, and you see that's quite well. But you also see that if you now zoom out to the second and the third plot, then it's definitely not perfect. Right? So the linear summation definitely helps you get into the anti-Stokes phase, but not too far. If you now do the quadratic summation, you get the plot on the right here, and you see that it works a very long way into the anti-Stokes phase. So you clearly see that there's a phase transition, right? There's a very clear jump in what the free energy does. And you can follow it, well, essentially all the way into the anti-Stokes phase. The reason that it's not perfect on the left is that I'm plotting t here on the horizontal axis. And when t gets large, gs get large. And so the gs corrections that I did not take into account yet actually start playing a role here. But if you would add those, then, well, I haven't done the computation, but I'm planning to do it, and I'm expecting this to be a perfect red line on the black dots. You can also do this for the RNs, and this is what I started with, right? This erratic behavior that you originally saw now has a complete understanding, because the lines now actually follow these very erratic looking points. So to wrap up, maybe a few remarks about theta functions. I won't have time to say a lot because I'm supposed to end already, but I won't leave you without mentioning theta functions at all. So just in a few words, of course, summing something that looks like q to the n squared over n should remind you of theta functions, right? It really looks a lot like a theta function, except for these Barnes-like coefficients. So we started wondering, is there actually a relation with honest theta functions? And this is very suggestive, of course, because people have found theta functions in matrix models before. I'm giving you some references here, starting with work by Bonnet, David, and Hénard, who actually showed that if you do something very different, if you, let me skip a few slides, if you take your partition function of the matrix model and expand it around a point where all three the cuts are filled, so this is really like starting in the anti-Stokes phase, then you can actually write this as some sort of theta function. So you can expand then around this filling fraction that you've chosen, look at other filling fractions, and you will find something that not only looks a lot like a trans series, but also looks like a theta function. So the coefficients in this quote-unquote trans series like thing that you find actually are quadratic in n and k. And so you get something that really is a theta function, this time without the Barnes numbers. And this is where the spectral curve computation comes back again, because now you want to compute, of course, the coefficient in this theta function-like object, and those turn out to be easily computable from the spectral curve. They are, again, just integrals over the spectral curve. So the upshot of the story here is that we find this Barnes-like theta function from one end, this actual Siegel, Riemann, Jacobi-like theta function from the other end. And the question is, are these two really the same objects? And the answer we're pretty certain now is yes. And this is the work that still in progress, so I'll tell you more about this in the paper that's about to appear. But there are a lot of good signs. The Q's that you find in the actual theta function exactly reproduce the Q's of the transseries, for example, if you take the one-cut limit. The Barnes factors you can also understand, because to describe this theta function in the limit where cuts go to 0, it's actually divergent, it turns out. And already in this paper by Marinho, Schiappa, and Weiss, they figured out how to cure that divergence, which is dividing by the Gaussian matrix model with the same number of eigenvalues. If you do that, you get something nice and smooth. But of course, then to reproduce your old computation, you have to plug back in this Gaussian matrix model. And if you know something about matrix models, you will know that the Gaussian partition function is actually the Barnes function. So this is where these Barnes numbers appear to come from. So this seems to work very nicely. And well, if you have questions, I'm happy to talk about it a bit more in the aftermath, or you can always hopefully soon read the paper. So to conclude, we've seen that these matrix models are really good toy models to apply resurgence to study phase transitions, for example. And you really need the resurgence to go from one phase into the other. You really need the transseries and to resum the transseries to go into the anti-Stokes phase. And you need this clever reordering. You need to know how to sum the transseries, and it basically tells you itself that it wants to be summed quadratically and not just linearly. So you need to collect the correct terms for this to work. And then you find these Barnes theta functions that are very similar to the theta functions that other people have found and that can actually be related to them. Then you might say, well, why not just study the theta function to begin with? Well, first of all, because then again, you're only in one phase, and then you need to figure out how to go to the other phases. But also because a transseries is very good at computing GS correction. So if you want to go beyond leading order in GS, it seems that the transseries is a much better tool for that than the theta functions, just because spectral curve computations can be very hard, and just turning the crank and computing a transseries can be very easy. So there's many open questions. We want to really work out in detail what to do with these Barnes numbers and how to sum things that grow have Barnes growth. And we have some ideas about that already. So hopefully that'll be in the paper as well. Of course, I haven't mentioned the trivalent phase yet, and it would be interesting to go in there as well and see if still the theta function, the transseries works. We would like to relate this to the two-cut transseries because they both should follow from the same theta function. And of course, any other examples where this quadratic summation plays a role, or even cubic or whatever summation would be interesting. So I'm already 5 minutes over my time, so let me stop there and see if there's a question. Thank you for your attention.
Thank you for the very pedagogical talk, as usual. And honestly, you were basically only 3 minutes over because we started slightly late. So yes, I would like to ask now if there's any questions. So David, I can see your raised hand.
Yeah, this is a true stupid question raised out of deep ignorance. All the time you were showing us how you're using the transseries to get to your red line. Where did your red line come from? Was it expensive to find? And if it wasn't expensive to find, why did you need the transseries?
The red line came from the transseries. Yeah. So, well, it depends on which red line, but some of the red lines are really summing some perturbative terms plus some non-perturbative terms, and then doing that as a function. So that was easy.
Sorry.
Yeah.
So, but the stimulus that you had visually watching down there was how could you get your dots onto the red curve? Yeah.
I would say the other way around. The dots are given. So the dots come from numerics, right? So I started with this recurrence relation between the RNs, and I have to go back a very long way. I'll talk while I'm doing that. And so these RNs you can compute numerically, but of course, to do that, you first need to fix everything, right? You need to fix GS, you need to fix capital N, you need to fix lambda, all the parameters in your model you compute, you fix, and then you can compute the individual RNs. And of course, if you're interested as a physicist, maybe in solving one very particular system that corresponds to certain knobs that you can turn in your laboratory, that's fine. And then you can just work with the dots. But now the question is, how can we understand this generically as a function of GS and as a function of lambda and so on? And so then you need some sort of function. And those functions come from the transseries. So that's why we introduced the transseries, to really see how things change if GS changes and how things change if lambda changes.
Thank you.
Any other questions? I do have a question, but if anyone else has anything. So one thing you mentioned, that to go to the trivalent phase, we would probably need two parameters.
Yeah.
But you also mentioned the two-cut phase, but wouldn't we need the two parameters to go to the two-cut phase as well?
That's a very good question. I think if you ask Ricardo Schiatta, he might give a different answer than I would guess, because it's a bit of a guess. Well, let me start with the safe answer. The two parameters is definitely enough, and you might need both of them to go to the two-cut phase. Then again, for the theta function, okay, you have two parameters, but really they correspond only in the region where we're looking at to the 1 sigma of the one parameter transseries. And there's no further Stokes phenomenon, right? So what kind of happens, you saw that in, now I'm going forward again, in the picture that I showed, is that the only Stokes phenomenon that you have here, yes, this is a good picture, turns on sigma. So on the right of this plot, I have sigma equals 0. On the left of the plot, I have sigma equals the first Stokes constant, essentially. And then I can keep this all the way in the entire green region. So then the question is, if I now make another jump going into the two-cut phase, does that turn on the second parameter or not? And I honestly have no good reason to say that it doesn't, except for the fact that if you in the entire green region only need one parameter, it seems a bit strange to me that you would need two parameters in the light blue region. And this is different from the trivalent phase, because in the trivalent phase, you're really doing a very different Stokes transition to get in there. So yeah, I'm not going to end up this lot of mumbling with a yes or a no. I would put some money on the fact that you only need one parameter, but I might be wrong.
Okay, thank you. Any other questions? Otherwise, we'll stop the recording. I don't see any questions, so we can stop the recording